Welcome. In this session in linear data analysis, we'll explore the application of Fisher's linear discriminant, or LDA, to some artificially generated data. Here I've generated some data, and they have two labels. I'm indicating the mean of one label using a cyan X, and I'm indicating the mean of the other label using a red X. And we could perform principal components analysis on it, and the axis would be approximately this. Now let's explore Fisher's idea. Let's say that we've formed the within label scatter, and we're going to solve that as an eigenvector problem. And when we do, we get this cyan axis. So this would be the axis of that minimizes the within label scatter of these data. Fisher's other idea was that we explore the between label scatter. And when we compute that, it's this magenta line, and as we expect, that goes between the means because we only have two labels in our data. And Fisher's linear discriminant analysis would suggest that it is neither this cyan line nor this magenta line that are the axis that will best describe our data. When we use Fisher's linear discriminant analysis, we get this white line, and this white line is simultaneously optimizing the between label scatter and the within label scatter. It's doing this by maximizing the between label scatter and minimizing the within label scatter. When we then plot these data and we project them down onto this LDA axis, this is what we get, is that these data are perfectly separated according to their labels along Fisher's linear discriminant line. The slight offset here is only for visualization purposes. And we can then take the data, we can illustrate them using the colors, and we can show Fisher's linear discriminant as a separating hyperplane. Here I've chosen a position along the axis that maximizes the accuracy of the separation. So we can now use Fisher's linear discriminant analysis both to separate our data, and we can use it to develop a separating hyperplane.